Last week, we started chapter 7 and looked at the different types of formations that we can have, including our anticlines and synclines, looking at folds, monoclines, domes, and basins. And continuing on, starting on page 209, now we're going to look at faults and joints, which were formed by brittle deformation. Remember that our folds are formed by ductile or that bending deformation. So when we look at faults and joints, we're going to see what happens when the rocks actually break. So faults and joints are going to be our rock formations that are formed from brittle deformation. Joints are fractures in rocks. Faults are also fractures in rocks, but along faults, we can see where motion has occurred. In other words, there's going to be a disturbance where we can see how one piece of the rock that's broken off has moved relative to the other. So in this picture here, you can see what we refer to as this offset layer. So here's a layer of rock here, this kind of darker layer that you see here that's referred to as the offset layer. And you can see in between this crack or fracture here. So this would be considered a fault because these layers are now offset. One piece has moved relative to the other. And so our arrows here show how much or show the direction of slip. So this piece over here on the right has gone downward. It has slipped downward, okay? Or this piece over here on the left has gone upward. So we looked at ductile deformation in the first part of chapter 7 with our anticlines and synclines and the other types of folds that we looked at. You can also see here, we do have a fault here where we can see the displacement. So we do have brittle deformation here. But over on the left of the screen, you can see an area here that isn't a fault. There isn't a break or a fracture here. This would be considered a fold, ductile deformation like we looked at last week. Now we'll consider several different types of faults. Our first type of fault that we look at is called a dip-slip fault. This is when movement is going to be parallel to the inclination. The upper surface of the fault, or the rock surface above the fault, is going to be the hanging wall block. And then the rock body that contains the lower surface is going to be the footwall block. When we see vertical displacement that's going to occur along these dip-slip faults, they produce what are called fault scarps, which are essentially these long, low cliffs. So when we look here, we can see a fault. And we know that this is a fault by looking at our layers of sedimentary rock here, especially if we look at this dark colored layer that's right on top. We can see that we've had slippage here, okay? So the fault scarp, you can't really see from this angle, but the fault scarp is what is almost like a scar. It's gonna be where that hanging wall block dropped, and we see these layers here now, or basically the inside of these layers. And you can see the slippage here is going to be, in this example, the hanging wall block is going to slip downward relative to the footwall block. And so you'll have to pay close attention to these arrows that let you know the direction that the wall blocks, the hanging wall block or the footwall block, are moving. There are two types of dip-slip faults. The first type is called a normal fault. And this is what we've essentially kind of been seeing, in which the hanging wall block moves down relative to the footwall. So if we look in this, back at this image here, as the hanging wall block moves down, this is referred to as a normal fault. They are associated with tensional stress that is going to pull the rock units apart, either by uplift that causes the surface to stretch and break, or by horizontal forces that are opposing orientations. In the Western United States, we have faults that are associated with these, what we refer to as fault block mountains. They can cover many square miles of territory and produce basically these kind of small mountain ranges. In the Basin and Range Province, which is in Nevada and in the surrounding areas, the crust has been elongated and broken. So we see these dip-slip faults to create more than 200 mountain ranges, essentially. And so we call these fault block mountains. The uplifted pieces of the blocks are called horsts, and then the drop down blocks, or the dips or valleys, are called grabens. So we looked a little bit there at our normal dip-slip faults, in which the hanging wall block is going to drop down relative to the footwall block. Now we'll look at what we refer to as reverse faults. In a reverse fault, the hanging wall block moves up relative to the footwall block. So we call it reverse because it's the exact reverse direction as we saw in the normal fault. And then a thrust fault is a special type of reverse fault that has an angle less than 45 degrees. So the overlying plate moves almost horizontally and can even cause an overlapping plate. Thrust faults are most pronounced among the convergent plate boundaries. And so this creates compressional forces instead of the tensional forces that we looked at in normal faults. And the colliding plates will create folds as well as these thrust faults. And some of our mountain ranges have been created by these types of faults, and we'll discuss those a little bit more later on. So in a reverse fault, again, you have to look at your directional arrows here that show that our hanging wall block is now moving up relative to our footwall block. And again, this is due to the compressional stress, okay? And then a thrust fault, we get, again, compressional stress, but at a much lower angle, so it produces these folds that occur as well as the fault. An example of a thrust fault. Another type of fault that we can have is a strike slip fault. So we looked at 3 types of dip slip faults: normal, reverse, and thrust. And now we're going to look at strike slip faults. Strike slip faults have movement that is horizontal and parallel to the strike of the fault. So we don't get the tensional forces or the compressional forces like we see in dip slip. Strike slip faults are going to move parallel to one another, or the 2 pieces of rock are going to move parallel to one another. When we look at the types of strike slip faults, we have right lateral and left lateral. The San Andreas fault is an example of a right lateral fault. It causes the block on the opposite side of the fault to move to the right as you're facing the fault. So if you're staring at the San Andreas fault, the opposite piece will move to the right. So that's a right lateral strike slip fault. And then a left lateral strike slip fault is the complete opposite. As you're facing the fault, the opposite side of it is going to move to the left. And an example of that is the Great Glen Fault in Scotland. Now, transform faults, we looked at these when we looked at earthquakes. That transform faults are strike slip faults that are between 2 tectonic plates. So all transform faults are strike slip faults, but we only call the ones transform faults that are in between the plate boundaries. So we looked at these, in chapter 4 when we were looking at tectonic plates, and then also in chapter 5 with earthquakes. So here is an aerial view of the San Andreas fault. Okay, and again, it is a right lateral fault. So if we're standing here looking at the fault, we will see this side of it is moving right. Okay, and we can kind of see in this figure here, part A, is some of the features that are associated with the larger strike slip faults. You can see we have, offset drainage, our valley here that we see kind of in between these. We have what's called a sag pond, which is partly due to this offset drainage and offset stream channels that we have. So you can observe these features when you look at these strike slip faults. Now, so faults are fractures in rock where movement occurs. Joints, okay, remember, are fractures where there has been no rock movement. They're some of the most common geological structures that we can find. We can see these in just about every rock outcrop. Most joints occur in parallel groups. Most joints occur when the rocks in the outermost layer of crust are deformed by tensional stresses. They stretch the rock layer and they cause it to break. Again, we know that breaking is due to brittle deformation. One way in which the rock layers are stretched is in response to regional upwarping and downwarping of the Earth's crust. And we can see an example of this in Arches National Park, which is in Utah. In this image, you can see that there are kind of two sets of joints, really, because you can kind of see a large joint that runs kind of through the middle, where you see this dark area over here to the right. But then you can see all of these fractures within the rocks. They were formed by regional upwarping. And this is Entrada sandstone. And so the this is a very rigid type of rock. And as the upwarping occurred, it caused the sandstone to fracture. You can see that the dominant joint set are marked with these arrows here, where you can see exactly where the jointing and breaking actually occurred. Joint patterns can also affect the weathering and erosion of bedrock. Now, there isn't a picture of this in the presentation, but on page 213 in your book, you see some other topography of Arches National Park. These are referred to as fins. So you see there in the geologist sketch, you've got this upwarping that occurs and stretching like we see here. And so we get the fracturing, we get these joints that are occurring. So what happens then is we're going to get weathering and erosion. So water and snow are going to get down into these cracks, and it's going to start to wash away the sediment. And so the joints are going to become wider and wider and wider until you eventually get this structure called a fin. And so this is, you see the two pictures there. You have an aerial view and then you have a ground view of the fins. So when you look at that ground view and you see really all of these separate structures, you kind of have to keep in mind that at one time, it looked like this. It looked like a solid structure. But due to weathering and erosion, we get these kind of individual columns of rock. Now we'll switch gears and get into mountain building. So mountain building has occurred in both the recent geologic past as well as older times back into the Paleozoic age. During the recent past, we have the American Cordillera, the Alpine Himalaya chain, and then in the Western Pacific, as we see around Japan and the Philippines. As we look at some older mountains, we see the Appalachians. These are from the Paleozoic age. They're eroded and less prominent. So the Appalachians are not as tall and as prominent because they've had millions more years of weathering that has occurred that has lessened their height over time. So the process of building a mountain belt is called orogenesis. Oro is the root word for mountain, and genesis is to begin or to produce. So orogenesis is what actually produces, or it's the collection processes that produce a mountain belt. Most major mountain belts display evidence of compressional forces that shorten the crust horizontally while thickening it vertically. And so these are collisional mountains. They result from the collision between one or more coastal crustal fragments into a continental margin, or from the closure of an ocean basin that results in continental collision. Collisional mountains are going to contain large amounts of sediments and sedimentary rocks, and that were folded and faulted. And so we can see this folding and this thrust faulting associated with orogenesis. So here we can take a look at the Earth's major mountain belts. So the ones kind of in this pinkish brownish color here, these are our younger mountain belts. And so you can see the what we refer to as the North American Cordillera, all the way down into the Andes Mountains. And then from the Atlas and Alps, the Caucasus, the Zagros, all the way over to the Himalayas. And then as we look around this island arc here from Japan all the way around through the Philippines. Then we see our older mountain belts like the Appalachians, one there in Greenland, the Caledonian Belt, the Ural Mountains. We see the Shields, and then stable platforms. So these kind of more in the middle of the continents. So when we look at mountain building, we're going to look at several different types. And so our first type is island arc mountain building. But kind of keep in mind, as we're looking at how these mountains are built, kind of keep in mind this idea of subduction, which remember is when one piece of crust goes below another. So when we have oceanic lithosphere that subducts beneath oceanic lithosphere, we get this volcanic island arc. And we looked a little bit at that in chapter 6 when we were talking about volcanoes. But when we have subduction of the oceanic lithosphere under continental lithosphere, we get a continental volcanic arc. And so we get mountains that occur along the margin of the continent. The crustal elements can't really subduct to any great depth. They're too buoyant. They want to float essentially on top, and they become stuck to the overriding plate. And if this subduction process occurs long enough, then it will close the mountain basin and lead to collision of two continents to build mountains. So now, island archetype mountain building, these result from that first experience or first scenario that I described. Steady subduction of oceanic lithosphere under oceanic lithosphere. And associated with this subduction zone, we're going to have volcanic activity. We'll have the placement of igneous plutons. Remember, those were the basically the hardened magma that accumulates under the crust or deep in the crust. And then the accumulation of sediment that's going to be scraped off of the subducting plate. And this then will increase the volume of the overlying plate. Those are essentially going to be stuck together. And so the overlying crust is going to become thicker. The continued growth of this type of island arc generates mountainous topography, primarily composed of igneous and metamorphic rocks, again, associated with that heat and water that's being driven from the subducting slab. And you can see this image on page 215, figure 7.24, where we get the subducting oceanic slab going underneath another oceanic slab there at that trench. And we get these plutons, we get magma coming in there, the production of these volcanoes, and you'll notice the sediment starting to build up. And as that sediment builds up, we can eventually get to a point where the islands are visible, on the surface of the ocean. Now, when we look at the Andean type mountain building, this is that second scenario that I described where we get subduction that occurs between an oceanic lithosphere and continental lithosphere. And we name this Andean type because we see a perfect example of this in the Andes Mountains. It's associated with long-lasting magmatic activity, and it builds these continental volcanic arcs. We get crustal thickening, and the oceanic lithosphere here has to be dense enough to sink below that continental lithosphere. So in Andean type mountain building, there are essentially three major steps that kind of have to happen here. So the first stage is having these passive continental margins, okay? So what we have here is our continental lithosphere. Okay, and so here's our continental shelf where our ocean is going to begin, all right? And you'll notice in between the continental shelf there, right associated with the continental shelf, you'll see these layers, these different colored layers that are starting to build up there. So those are shallow water, sandstones, limestones, and shales. So we're starting to get this layering of the sedimentary rock here, and at some point a subduction zone is going to form here, and so that takes us into our next steps. So as the oceanic lithosphere starts to subduct, okay, so we get this subduction zone that is going to build. As it descends down into the mantle, we increase temperature, we increase pressure. And this drives water out of the oceanic lithosphere here. And so this water is going to start coming out of that. And it's going to continue all along this little area here into this region here right beside the trench. Okay, where you start to see all those layers that are being folded there. These also will reduce the melting point. We get partial melting here. And as we get partial melting, we start to build the magma chambers. And we get some plutons in here, and this is going to lead to the creation of our volcanoes because these magma chambers are going to start to rise upward toward the top of the continental crust. We get continued compressional forces thickening this crust. If you'll notice where these magma chambers are, we're continuing to thicken the crust. We're making this area here, this kind of light sandy color here, thicker. And this starts to elevate our mountain belt here. So we get the associated volcanoes because of these underlying magma chambers, but we're also getting accumulation of the crust. And then we're going to continue this. We're going to get plutons as these magma chambers close. Subduction is eventually going to end, and these plutons are going to make their way to the surface, forming the batholith that we can actually see on the surface of the crust. The other thing we get is what we call an accretionary wedge, okay? All of those layers of sediments have now been pushed upward by this expanding crust. And so we have uplift of this, and that is called the accretionary wedge. And in between the two areas, so here's our batholith, so here's our mountains that are being formed over here on the right. We've got our accretionary wedge over here on the left, and in between them we've got a basin. So we've kind of got this sunken area here as a basin. And so essentially what happens is sediments accumulate here by the batholith, sediments accrue over by the accretionary wedge, and we get this four-arc basin here. And we see this in the Sierra Nevada and coast ranges of California and Washington and Oregon. Now, as we move into our third scenario, we have the collisional mountain belts. We have the Cordilleran type mountain buildings. So these are the newest mountains that have been built. And this is our first example. So the Cordilleran type orogeny, which is named after the North American Cordillera, that young mountain range, is associated with the Pacific Ocean. It's unlikely to close because there is a seafloor spreading. You know, there are divergent plates in the Pacific Ocean, so it's spreading at the same time it is subducting. So the Pacific Ocean is unlikely to close. So we get island arcs that have been created along with small crustal fragments that are just going to be carried along by subduction until they collide with the continental margin and then accrete or join into it. And this has generated some of the mountain ranges that rim the Pacific. And terrains, which are these fragments of this material, make up a lot of the Western United States. And this, in the map on page 219, you can see these terrains. In red, you've got all of these oceanic terrains. These used to be in the ocean. They used to be part of the ocean. They were formed there. And then over time, they collided with the continental crust on the Western United States. Some terrains were microcontinents like Madagascar. Some were island arcs like Japan. There are about 100 of these that still exist. Now we'll look at another type of collisional mountain belts with our alpine type mountain building. And this is the zone where two continents collide. So with our Cordilleran, it's when pieces collide. So these island arcs or microcontinents. So now we're going to look at what happens when two whole continents collide. And alpine type orogenies are named after the Alps, which have been studied for more than 200 years. Mountain belts formed by the closure of ocean basins include the Himalayas, the Appalachians, the Urals, and the Alps also. These types of collisions resulted in mountains that are characterized by laterally shortened, okay, and vertically thickened crust. So we get slivers of oceanic atmosphere in there as well. We get what we refer to as a fold and thrust belt. And where these two continents collide and where they're essentially welded together is called a suture. Now, when we look at the Himalayas, the orogeny began between 50 and 30 million years ago or so when India began to collide with Asia. And as India slammed into Asia, it created this uprising that developed into the Himalayas. the last thing that we have now is to look at the Appalachians. They run from Alabama all the way up to Newfoundland in Canada. Mountain belts of similar origin also exist in Britain, Scandinavia, Africa, and Greenland. And so this provides some evidence that we had a mountain system that covered all of these areas at one time. It resulted in the assembly of the supercontinent Pangaea. And there were essentially 3 distinct episodes of orogeny that occurred during that time period. So we're going to watch one last video here showing us how the Appalachians were formed. So that brings us to the end of chapter 7, looking at our different types of rock folding and breaking and fracturing that we can get.